Hello everyone, and welcome to our online training for students presented by Doolittle Software. Today we will be working with our FEA and design software RFEM, and the goal of this training is to go over the fundamental knowledge needed so students can model and work with any type of basic structure, view results, and understand the fundamental basic theories. In this training we will be focusing on simple models mostly. My name is Alex Bacon, and I will be your trainer for today. I am a technical support engineer, and I am also joined with my co-organizer, Amy Heilig, who is the CEO of the U.S. office and a technical support and sales engineer, and we are located in Philadelphia, PA. Here's the control panel. This will be used throughout the training, so you can hide this panel as well as adjust audio settings if you need to. There's also a box with a handout, and that includes the PowerPoint. Later on, after this training, we will be sending out an email for PDH certificates, and that'll take about a day. And that will also include a link to the recording of this training as well as the models. So another thing is to also, if you need to ask a question, is to use the questions section within the panel. And when you do that, me and Amy, or Amy will interrupt me and let me know there's a question, and then we can answer your question. There will also be 2 5-minute breaks. There will be one at 11 a.m. and one at 12 a.m. or 12 p.m. I'll try to make these exactly on the dot, but they usually will be around that time. The content for today's training will start with principles of FEA software, and then we'll go into an introduction of RFEM. The next thing we'll be going over is a model, and this will be the introduction example for continuous plates, and that will involve plate theory. After that, we'll go through a stability analysis example called Euler Case 1. Then a moment frame will be converted from that stability analysis, which we can analyze and go over the results. And after that, we'll be going through a concrete model. Usually the concrete model, we will maybe be able to start, but we might not get all the way through it. So to begin, we'll be going through the basics of FEA. So for the basics of FEA, computer programs are based on the displacement method. And another method you may be aware of is the force method, where the unknown is the force, and then you can calculate the internal forces based on that. Another example is the displacement method, where the unknown is the displacement, and this involves first calculating the displacement vectors and then the internal forces and support reactions. So basically, an analytical solution is difficult with large, complicated structures. So doing hand calculations for large structures can almost be impossible and feel like a daunting task. And the limits are being reached when it comes to that, and it's also hard to receive accurate results. So this is where an FEA comes in and is then required. So the structure within an FEA is converted to finite interconnected element mesh, and then the material and cross-section properties are given at each finite element node. And then once that's done, the mechanical behavior is transferred between these elements. And so a word I'd just like you guys to remember or walk away with is discretization. And this is where the structure submeshing is, or the structure is being submeshed into finite elements. So now we can go through the FEA calculation workflow. So first, the determination of the local element stiffness relations are the properties is determined. And then the program changes the stiffness relation at each node to the global coordinate system. Then the entire structure is assembled. And then fourth, the support conditions are implemented into the structure. Then the displacement vectors are determined. And lastly, the support forces and internal forces are then determined. So now I just have a quick question that I would like you guys to answer that I'll give you about 30 seconds to a minute to answer, and then we can go over the answer. Oops. Sorry about that. There we go. Oh, wrong question. There we go. Yeah, so if you guys could just answer this question, and then we'll go over it in about 30 seconds. Okay, awesome. So it looks like mostly everyone said A, a couple C's, a couple B's, but the correct answer is A. So what is discretization? And the answer is a structure that is converted into finite elements, or that is the method of converting structures into finite elements. So that's good. It looks like part of my pronouncement, yeah, Amy answered that, so good. Yeah, if I'm breaking up or anything like that, it might just be your internet connection. So maybe give it a couple minutes and see if that solves the situation. Okay, so now we can move on and do an example. Actually, I have one last question before we move into the example. Actually, sorry about that. We'll go over that question. So yeah, now we can move on to the example, and we can start by modeling the continuous plate. So now I'll move into RFEM, and right now you can see that we have our continuous plate here, and this is what we're going to be modeling with an RFEM. And with this continuous plate, we can compare the results of the bending moment with a continuous beam. So now I will just move into RFEM. One second. And now you should see RFEM. And right now I have an example up, and with this example, I will just be using this so we can go over the UI of RFEM and just the basics like tools and everything. So to start off, RFEM is a structural analysis software capable of analyzing plates, members, and solids. Deformation, stresses, and internal forces can then be calculated for a 3D structure. So just to go over again the basic UI, the project navigator on the left-hand side here, this panel, this is called the project navigator, and this is very important for model data and this includes all of your model data, everything that's modeled within your structure. And for example, within this project navigator, things like members, you can expand and collapse all of these folders, such as members, and within these folders we have each member listed. This can also be done for nodes, lines, and materials, etc. And you can see when I click on any member within this dropdown or within this expanded folder that this is synced up with your graphics window on the right hand side here. So if you ever need to find anything, you can do it easily with that. The next thing we have is our tables at the bottom, which mine are hidden right now. And if you have either your project navigator or your tables hidden, you can show or hide those using these two buttons up here. So I can click and hide and show, and you can see that we have the tables down here, and these tables can be, within these tables, things can be created or deleted, and you can also just view your model information, and you can see that the tables have tabs down here to organize all of your model data, as well as we have different tables for things like load combinations and results. Next, if you want to change your background, you can do that as well by going up here to Options and Configuration Manager. So we can open that, and you can see that right now I have mine set to a standard white background, which I will use for this training. But you can also change it to a black background, and we also have a couple other options as well. After that, another thing to go over is this is called the work window here. And within here you can draw lines, surfaces, etc. We'll be going over all of the finer details with that. Then up here you have your toolbar, and this includes all of your tools and everything, which are organized within different subcategories. And if your toolbar maybe looks a little messy and you just want to clean it up, you can right-click anywhere within this gray space, and you can go down here to reset the default, and then you can click yes, and then your toolbar will look like mine if you're having trouble finding the tools. Next, we have our insert menu, and this is another way to basically insert things like model data. You can see we have a long list of model data here, from nodes to line hinges, and then we have also a way to insert loading and load combinations, but again, we'll be going over this in more detail later in the training. So, and then to change your view, you can do that with these tools up here. Right here we have our view in the X direction, view in the Y direction, and the Z direction. We also have an option for isometric view as well, so we can click on that, and you can see that we can change our view with these buttons. Next, we have our add-on modules, which are our design modules you'll use to design your structure as needed. You can see we have a long list of them. And this is one great thing about RFEM, is that your internal forces and everything from your model will be designed in these add-on modules. So basically RFEM analyzes the basic internal forces and deformations, and those are imported into any of these add-on modules, which if you're a student, you should have access to all of these. So we'll be just going over a couple of those later on as well. Next, we have our display tab down here. So within our project navigator, we have a couple tabs at the bottom. This first tab is for data. The second tab is for display. So within this display tab, you can basically turn on and off graphically anything you'd like within the work window, and you can see that we have this universal language of expanding and collapsing folders here. So for example, if I wanted to turn off, I don't know, surfaces under model, I could do that, and that'll turn on and off my surfaces. So lots of options, lots of customization there. The next thing, our last tab here we have is our views tab. So within our views tab, we can create visibilities based on these options down here. So if we turn on visibilities, we can create visibilities based on member cross-sections. So right now, if I only wanted to show my W18 by 50 here, I could do that. Maybe I only want to show my rectangular columns here or rectangular cross-sections, my 12 by 12s. We can do that as well. And then you can also save visibilities as well, and then pull them up whenever you'd like. The third tab we would have is our results tab. So if I just run the results for this model quickly, then we will see our results tab, and that will pop up at the bottom here, only if we have results ran. So I just ran my load combination 1, and if I turn off my visibilities, and then now you can see in my results tab, this is again similar to the other menus where we have our expanding and collapsing folders. So right now I have global deformations checked off, and we're viewing our resultant deformations. And you can see we get a nice look at that, and then we can also check out our member basic internal forces, as well as our basic internal forces for our surfaces as well, if we would like. But we'll go over more of this in detail later, so don't feel too rushed to learn this real quick. We will be going over all of this in the training. But just want to give a basic overview. Also, controls, very important. So if you like to interact with your model, if you have a scroll wheel on your mouse, you can zoom in and out with the scroll wheel. Clicking down the mouse scroll wheel will let you move the model and translation. And then holding control and clicking down the scroll wheel at the same time will also allow you to rotate your model. If you don't have a scroll wheel on your mouse for some reason, you can use the arrow keys on your keyboard to move the model around in translation. You can also hold control and use the arrow keys to rotate the model as well. And then if you want to zoom in and out with the keyboard, you can use the plus and minus buttons as well. One more thing before we get into modeling, I would like to just go over highlighting. So real quick, if you highlight from right to left, this will give you a purple box, meaning that anything that touches this purple box will be highlighted and selected. Highlighting from left to right, only things that are fully engulfed into this red box will be selected. So that's the difference between the two boxes, or two highlighting boxes. So now, before we go into, I can go back to the PowerPoint. And I just have another question to ask before we get into the model. So the question is, what is RFEM? And then the options from A to C are listed. So if you could just answer that, and I will give you about 30 seconds to a minute. Oh yeah, I forgot to mention you can answer the question within the question box. Awesome, yeah. So it looks like mostly everyone is answering B, which is good. That is the correct answer. So some are answering A, 3D structural frame analysis program. The only reason that one's not correct is because RFEM is an FEA program, And within RFEM, you can calculate things like plates and shells and not only just members or a frame. So awesome. So we'll get into this into more detail about that and throughout the training. So now we can move on to our continuous plate model, and we can go back to RFEM and start with that. So I'll just go back to RFEM, and now we can begin with our continuous plate model. And the first thing we want to do is we want to open a new model file. So to do that, we can go up here to File and click New, or we can also just click on the New File, New Model button right here. So once you click that, you'll see that this new model general data dialog box will pop up. And within this box, we can enter the information just needed to create our model. So the model name, we can just name anything you want, but I'll just name mine continuous plate for this example. And I'll just put training. You can also add a description to your model if you would like. And then the next thing is our project name here. And with this, we won't get into much detail with this right now, but if you have a project and you have a lot of models that go with that project, you can create just a project folder, and this will be a local folder on your computer where all the models you create will just save to that folder automatically. It's a good way to stay organized. The next thing is the type of model, and right now we'll just leave this as a 3D model. And then classification of load cases and combinations. This just allows you to create load cases and combinations automatically if you have this box checked right here based on any standard that we have listed here. So you can see we have lots of international standards you can pick from. I'll just leave mine as the ASCE 716 for this training. And the next thing is our positive orientation of our global z-axis. We'll leave that as upward as default. And you always want to make sure that the local z-axis is set to downward. One last thing before we move out of the general data is I would just like to point out that if you are using metric, that you can change that. You can change the units in RFEM to metric or imperial. For this training, I'll be using imperial, but if you want to switch between them, you can click on the units button here in general data, and then you can go to this load saved profiles. You can check off metric, and then once you check off metric, you can click OK. Or you can also just double click on metric, and that'll change your units to metric. But again, I'll use imperial for this training, so I'll click OK. And then I'll click OK again out of the general data dialog box. And now you'll see that we have a grid here, a blank grid in our work window that we will be using to model our continuous plate. So the first thing we want to start off with is creating a rectangular concrete surface. The first thing we can do is we can either do that by going to Insert Model Data, and then you can go down to Surfaces. Or what we can do is we can click on this button right here called New Rectangular Surface. And now that I have this up, we can customize the thickness of our surface we can customize the thickness of the surface as well as the material. So right now, I will leave this as 8 inches, but the material I do need to change to concrete 4000 psi. So to do that, I can click on this button here called Import New Material from Material Library. And once I click that, you'll see that this window here pops up for our material library. And this is pretty simple. You just want to start with this left-hand side filter here where you can start off with, I want concrete. It's the materials, so then also material category, regular, normal concrete, standard group. You can see we have a bunch of standards to pick from for the type of concrete you're designing. For this, I'll just be using the ACI as for an example, and then I can click and pick the latest standard for that. So I'll select 4000 psi. You can see we have our material properties down here. We can click OK. And now everything in this window is basically filled in that we need, and we can click OK. Now you'll see that your cursor or my cursor will turn into a reticle. And what I can do is I can just left click anywhere within this grid. You can see that the reticle snaps to these grid points here. And I can click, and then I can draw this surface here. And this surface is going to be 32 feet by 16 feet. So I'll go 32 feet in the X direction, and then 16 in the Y direction. And then I can just click, and you can see that this surface has now been created. One thing I did want to change, so if you need to edit your surface at all, or anything that you place within RFEM, you can easily edit it by right-clicking on it and going to Edit, or you can also just double-click on it. So I do need to change the thickness of this plate to 12 inches. So I can easily just do that by simply double-clicking on it, and you can also see you can change your material and other things as well. So I'll click OK. And now we can create the same plate again above this original plate. I can just go up here to my rectangular surface tool again. I can click OK. And now I'm going to model a second plate 5 feet above this one. And then I can click and just drag my cursor. Make sure that this is 16 feet wide. So that will be right there. So now we have our two plates here modeled within the XY plane. If you ever, well, we'll go over work planes later in the training. So then we can simply create a third plate pretty easily. And to do this, we can use our move and copy tool. So what I can do is I can rotate here, and I can simply just highlight the second plate, and I can right click on it, and I can click move/copy. And what this will allow me to do is I can make a copy of this plate and then just move it wherever I would like using displacement vectors here. I can also, what I'm going to do is use this select 2 points and return, and this will give me a displacement vector by selecting the 2 points graphically. So now I can just simply create one copy of this plate, and then I can create a displacement vector graphically, and I'll select my bottom corner here, and I would like this copy to be 5 feet above this plate. So I'll click that, and I'll click OK. And now you can see that the copy was made, and it was made based on that displacement vector that I selected. So the next thing we want to do is now we can create our continuous beam. And to do that, we can just create, basically we're just going to be creating our member. And you'll see that my plate is hanging off the edge of my grid. So to change the amount of grid points that you have, or to expand this grid, we can simply go up here to our tool. It's not really a tool, but our settings for our work plane. We can click on this. And now you see we have a box here, a dialog box with a lot of options for our work plane and grid settings. So the one thing we're just going to be focusing on with this is the number of grid points. So you can see we have a graphic here giving you an idea of what these values represent for plus and minus and 1 and 2. We have 50 grid points basically in our negative x and positive x and negative y and positive y directions. So you can either just change these numbers and expand your grid manually. Another good option is to just check off the dynamically according to size of model. And when you check that off, you can click OK. And now you can see that the grid just basically changes depending on what you modeled, which is pretty useful. So now we want to model our continuous beam. And to do that, we can just simply go up here to our tool called New Single Member. And we'll click on that. And then once we click on that, we have our new member dialog box here. And we have basically a lot of information, but the one thing to focus on is just to input what our cross-section is going to look like. So we can just go over here to this button called Import from Cross-Section Library. We'll click on that. And then this is similar to the material library, but you can see that we have our cross-sections here. We have rolled, built-up cross-sections, parametric thin-walled, parametric massive, and parametric timber cross-sections, as well as some other options down here as well. Right now we'll just be focusing on our rolled I-sections here. Actually, my mistake. We will not be using the rolled I-sections. We're going to be using the, right here, the rectangular parametric massive sections. So we'll click on that. And then once I click on that, you can see that I can enter the parameters for my cross-section, like the dimensions. So I can enter what the base is going to be, which is going to be 40 inches. And then my height is going to be 12 inches. And now you can also see down here that our material is by default set to 4,000 psi concrete. So it's also per the older ACI standard. So what I can do is click on edit, and then I can go and change it to the newest standard, change it to 4,000 psi concrete, and everything is correct there. So we'll click OK. We'll click OK again. And now you can see that we imported that cross-section. You can see it's represented here on the right-hand side. So everything's good there. We can click OK. And now we can simply just draw our cross-section on our grid here. Again, the cursor snaps to these points. And I'm going to add this beam 5 feet away from my third plate here. So I'll left click, and now you can see that I can just draw, you see this line here, I can draw my beam, and it's going to span the same length as our plates here. So I'll left click again, and now you can see that our beam has been drawn. And now we have our 3 plates in our continuous beam right here. So the next thing we want to do is we want to divide these lines here on the edge of our plates. So we can add a midspan here for supports. We also want to divide this continuous beam so we can add a middle support as well. So to divide the lines, we can simply just right-click on the line. And again, when you right-click anywhere or on any object, you get this shortcuts menu. So we can just right-click on this line to divide it. And then we want to go up here to divide line. And you can see under divide line, we have multiple options for dividing a line. So we can do it by distance. And you can see when I pick that divide line option, we have these gray arrows here on your lines. And these arrows tell you the orientation of the line or the direction that you drew the line. So this would be the start, and this would be the end of the line. You can also view these arrows by just hovering over any line that you've drawn. So right now we just want to put a node or divide this line in the middle. So within this box here, you can see we have line 1 selected, and you can see that we can pick where we want to divide it. We want it to be at 50% or 16 feet, halfway down the line. So we'll click OK. And now you can see that a node was placed and this line was divided. Now we want to do this for the rest of our lines here. So this one, I'm going to right click and do the same thing. And I'll choose a different option. So maybe you want to divide your line by n intermediate nodes, which just means you can tell the program how many nodes you want to place on the line, and it'll divide that line equally depending on those nodes. So I just want to place one node. I'll click OK, and now you can see that that one node is placed and equally spaced. So now we can do this for the rest of the lines, and we can easily just hold Control, and we can just select the rest of these lines here. Right click. So holding Control and clicking on or selecting options will allow you to select multiple options. And then we can just do this by a distance again. Everything's set here. You can see the multiple lines have been selected. I'll click OK, and now we have these nodes placed in the middle of our lines here. Now we would just like to divide our continuous beam up here, and I can just right click. It's similar to the lines. I can just right click on the beam, go to divide member, and the third option would be graphically. So graphically just allows you to select graphically where you'd like to place the node. I'm going to place it right in the middle here at 16. And now you can see that our member here has been divided. I'll rotate the model to get a better view. And now that our members and lines have been divided, we can draw, for our plates, we can draw a line down the middle of them. And the reason we are putting this line down is to later on add a line support there. So we have some mid-span support. So I'm going to, let me go back. So we have an option up here called New Line, right next to our New Single Member button. So I'm just going to click that. Now you can see this box opens up here, and what we can do is just draw our line within our work plane here. I'm just going to select snap to and select this first node here, and then I'm going to draw it and snap to the second node. And you can see we have a nice perpendicular symbol there letting me know that the line is perpendicular. And I can right click anywhere or hit escape to exit out of that tool. And now you can see that our line was drawn. So now that this line has been placed, instead of having to redraw it, we can simply just click on it and hold Control. And if I click on something and hold Control and then drag it, that'll make a copy of it. And this is a pretty great workflow for working with anything within, oops, let go of Control too much. So this is a great workflow for working with anything in RFEM. You can simply just highlight something, hold Control, and then make a copy of it and drag it and snap it to anywhere. So it's pretty efficient. So now we can add in the nodal and line supports. So to add in, first off, we'll add in our line supports for our plates here. And to do that, we can go up here to New Line Support. And this line support is going to have certain conditions to it. So what we can do is click on this button here called Create New Line Support. And you can see here that we have our support conditions down here for our supports. And basically, this first section here is for fixing your conditions and translation, or you can also fix your degrees of freedom and rotation here. And so for this example, we just want the rotation fully released. And that's basically all we need to do here in this box. So this will be just a hinge support. So we can click OK. We can click OK again. And now I can simply just click on my lines here. And I can click on the outside here to add supports to the ends. So we'll have two end supports and a mid-span support. And now our line supports have been added to our plates here. Now we just need to add nodal supports to our beam here. So we added line supports to our plates. Now we want to add just nodal supports. So to do that, we can go up here to New Nodal Support. And you can see by default that hinged is already selected here. So instead of having to go in and create a new nodal support type, we have just hinge selected already. So we can hit OK. And now we can select our first end node here, and then we can select our middle support. And this last end support is going to have different conditions than these two supports here. So we can go up to nodal support, and we can create a new condition or a new type of support. And this support will be the same as a hinge support, but the rotation about the local x-axis will be restrained. So I'll click OK again, and now you can see that that support is a little bit different. So it can't rotate about the x-axis, so it's locked. And now all of our supports are defined. So now that our supports are defined, we can get into loading. So now we would like to load these plates in this continuous beam. So it is important that we create a new load case because every load within RFEM needs to be assigned to a load case. So I can go up here to either edit load cases and combinations, or we have a button here called New Load Case. So I'm going to click on the New Load Case button. You can see the program has automatically created a new load case for me already. So this load case, you can add a description here. And for this one, I'll just call it dead load. And you can see the action category is set to dead. We don't need to worry too much about that right now. But right here, you can see we have an option for activating or deactivating self-weight. So for this example, I'm going to deactivate self-weight. And then now our load case has been defined. And we can click OK. So now you can see up here we have our drop down telling us which load case we're under, and you can see I had load cases and combinations automatically generated based off of standards. So now the program has generated some load combinations and result combinations, but we don't need to worry about that right now. We just want to stay under the dead load so we can add loading to these plates in continuous beam. So the first thing we want to do is create a new surface load for our beam or for our plates here. And to do that, you can see we have a couple loading options right here below dead load. We have some point loads, some uniform loads for members and lines, and then we have a surface load. So we want to add or click on this new surface load here. and this dialog box will pop up, and you can see, again, we can just work through these different sections here. So our load type will be a force, our load distribution will be uniform, our load direction, you can see you can pick from a couple options here. We'll keep ours as global related to the true area in the global Z direction. Just a quick something to point out, the local axes, if you ever see lowercase coordinates, those relate to the local axes, and the global axes are the capitalized coordinates here. So we'll keep that as the global Z coordinate. And now we just want to add a magnitude to our load. So this will be a magnitude of 0.2 and our 0.21 for our KSF. And now we can click OK. And once we click OK, you can see that my cursor has changed here, allowing me to select surfaces within my model. And once I click on a surface, you can see that those loads are being generated onto the surface. You can also notice that my loads are pointed up in the positive Z direction. I would like those to point down. So what I can do is simply just highlight them and double click on them. And then I can add a negative sign in the front of my magnitude here. And once I click OK, you can see that the loads will be shifted, or they'll be swapped. Next thing we want to do is add a uniform load to our continuous beam here. Again, up here with our tools, I want to choose a new member load. Keep in mind that the member load tool for loading is for members only, and the new line load tool you want to use only for lines when you're applying loads to the perimeters of surfaces, for example. So we'll choose new member load. And again, this is similar to the surface load, where we will have a force here. That's the load type. This load distribution is going to be uniform. And the load direction, again, is going to be in the global Z direction. I'm going to add in a magnitude of negative 0.21 for our kip. That'll be kips per feet. I'll click OK. And now you can see that my cursor has changed, allowing me to select my two members here. And now we can just right-click anywhere to exit out of that tool.
Hey, Alex, we have a quick question.
Okay.
The question is, how can you quickly edit the load? Let's say you put in the wrong load magnitude. So maybe you can show how to just quickly make changes to a load that you've already drawn.
Okay, yeah. So if you've drawn your loads here and you want to edit them, you can simply just double click on them. And once you double click on them, or if you just double click on one, that'll allow you to edit just one load. Also, you can simply, if you need to highlight all of your loads or a couple loads at a time, you can highlight them and then double click on them, and that will allow you to edit them.
Great, thanks.
You're welcome. Yeah, so now that we have our loading, we can now move on to creating FE mesh refinements. So within the program for surface elements, an FE mesh is generated, and right now our FE mesh is set to about 1 foot for the length of our finite elements. And we'll get into, if you're a little confused by that, we'll get into more of that later. But for now, we would just like to add an FE mesh refinement, which allows us to change the length of how fine our FE mesh is going to be for individual surfaces. So to do this, I can simply just right click on my surface here, go to FE mesh refinement, and then click on new. And for this, I'm going to just create a new FE mesh refinement here using this button called Create New FE Mesh Refinement. you can see that surface 1 is selected, so I'll click on that. And then right now we just have surface selected, which is automatically done by the program, and we can set our target FE mesh length. So I want to set mine to 0.2 feet. This is smaller than the 1 foot default that is already selected globally in the program. So I'll click OK. I'll click OK again. And now you can see right now that we have this little icon here giving us or telling us that an FE mesh has been applied. Now we want to do that same thing for our other 2 surfaces here. And we're just going to, again, we can right click on this surface and add one. But we can also go into our project navigator here on the left-hand side, and we can go down here and scroll to FE Mesh Refinements. I can expand that, and you can see we have one for Surface 1. I can right-click on FE Mesh Refinements and click on New FE Mesh Refinement. And now I can just click on Surface. It's wondering what surface I want to apply this to. I can type in the surface number, or I can select the surface graphically. I'll click OK. And for this surface, I just want to increase the FE mesh refinement just so we can get an idea and compare results later on to see how our results change depending on FE mesh length. So I'll click OK, and again, we get that icon, and then I'm going to do the same thing for this third surface. So I'll just right click on it, and then I'll create a new FE mesh refinement, and then I'll just make this 1.6 feet. So you'll see that they'll be increasing down the line. I'll click OK again, and you can see that that icon has been placed there.
We have another quick question unrelated to the FE mesh, which maybe you can just address quickly.
Okay.
One of the attendees noticed that you selected concrete for one of the materials. They're wondering, what does the RF concrete add-on module do then?
Okay.
How is the add-on module different, I suppose, from RFEM is what you could quickly explain.
Okay, yeah, so basically the material for concrete has been selected with RFEM here. And you'll see later on when I run results and everything that in RFEM you just get things like the global deformations, the internal forces, support reactions, etc. But if you want to design, let's say rebar, you want to design your slab here for reinforcement, that's when RF concrete members or RF concrete surfaces would come into. So we have 2 different modules, one for surfaces and one for members. So basically the add-on module is for designing the reinforcement is what that's for. So
yeah, and I would just add to that, just like what Alex said, the analysis is completely within RFEM, and all materials are available to you there for full modeling for the analysis. And then, as he mentioned, the modules are for design. So within the RF concrete modules, you would find the various standards, such as the Eurocode, the ACI, the CSA standard, to actually do the reinforcement design, which is not done within RFEM. So I think that's good. Thank you.
Yep, awesome. Thanks for the clarification, Amy. Yeah, so that was a good question. Yeah, so I think later on we'll be getting into some, but we can just move on for now to going over the sections. So we just want to add sections to these plates here, and to do that, we can use our tool up here for defining sections and result diagrams. So I'll just hit this drop down here, and now I can create a new section through the plates we have defined, and that will allow us to open this dialog box here and create a section name. I'll just name this one AA, and then from here I can select the point A to point B of where our section cut is going to be placed, and to do that I can click select edge points of the section here, and I just want the section cut to go right through the middle. of this first plate here. And you can see that there's an icon here, kind of like an AutoCAD, where you can select the midpoint of your line, and then you can do the same thing for the other line. So now that section cut, everything is good and defined. It's going through our local Z plane here in the positive direction. We have a surface selected here via plane, so this is all defined. We can click OK. And now you can see that that section cut has been defined there. And you'll see that these will come in handy for our results. Now we want to do the same thing for the rest of our section cuts. And instead of having to create multiple sections or multiple section cuts, again, we can simply just select on our section, hold Control, and then copy. And you can see that I can just simply create copies. Make sure you hold Control. I can simply just create copies of that section. And you can see that RFEM has automatically given it a new section name. You can change the section name if you do that within the project navigator by going over here to sections, and then you can simply edit a section and rename it. I'll make this one AC, and then my other section will be AB. Yeah, so click OK, and now everything is basically ready for calculation. So we have our surfaces and members along with our supports and loading. So again, you can turn off the loading, like I don't have mine shown right now, but you can turn on and off the loading up here with this button. I'll turn it off for now. And now we can go up here to our toolbar and we can click on this button called Calculate All. So once we hit Calculate All, the program will go through and run the calculations. It should only take about a minute or two. It all depends on the size of your model and the complexities. And then once this runs, the first thing we should see is our global deformations, and those should be shown. And then we can get an idea of our internal forces and our things like support reactions. So now you can see that we have our global deformation shown right now. You can see we get a panel over here on the right-hand side. And this panel is basically the legend for our colors here. And you can see that we have a max displacement of 0.022 inches. And then we can also view the deformations on our member here. Right now, we just have that set to a yellow line. But if we wanted to have a colored cross-section for this deformation, we could go to Display, and then we could go to Results, Deformations, Members, and we could select cross-sections colored. So now we get a nice color section here. We can also take a look at our member internal forces. So I can check member, and now I can just look at my axial forces. I can get a look at, right now we don't have any. I can get a look at our moments, and we can get a nice moment diagram there. And we can also take a look at our internal forces of our surfaces. So we can view the basic internal moments along the x-axis. And again, like I said, every element has a local axis. And again, this is referred to with the lowercase coordinate here. So if I hover over any element, it'll give me the local axes for the plate, along with the, also if we want to see the local axes of our member here, we can right click on that and click on local axes, and now we will get that for all of our elements here. So I can right click again. Yep.
Quick question. One of the attendees is asking how to find the optimal mesh for the analysis.
Yeah, okay. So the optimal FE mesh for analysis, it's a little tricky. So there's not an actual specific length that you would pick for your FE mesh for a certain model. So basically what you can do is adjust the FE mesh by going up here to calculate, and you can go to FE mesh settings. And what this is the global FE mesh settings, or for your model. And here we have our target length of finite elements, and you can change this. And so basically finding the correct FE mesh is basically just a guess and check. So what you can do is you can take a look graphically if you zoom into your model at the FE mesh and just make sure it looks good. But then also you can run the results of your model with a certain FE mesh length, and then you can change the FE mesh length or make it finer, and then run your results again and compare those results and see how much they've changed. And you can just keep doing that until your results don't change, or the difference between your change results is small.
Yeah, I think exactly as Alex had mentioned, it's basically just running a test and trial type process where you continue to decrease the FE mesh. And is that exactly as he says, if your results are changing significantly, then you know your FE mesh is not refined enough. The other thing I wanted to point out, if Alex, you can go to calculate FE mesh settings again. And the third tab is called adaptive mesh refinement. This is something that we're not going to get into today, but essentially the program will run that testing process for you. So here you can set the number of iterations, the load case or combination to consider, and the program will run a quick analysis in the background, check the results, and then it will refine the FE mesh in certain areas of the model, and it will essentially create the FE mesh that is optimal for your model. So this is a way to automatically do it. To manually do it is exactly as Alex had mentioned. So
yeah,
hopefully that answers the question. So thanks, Alex.
You're welcome. Yeah, awesome. Great. That's awesome to point out. It's a good tool to use. So yeah, fortunately we won't get into this training, but yeah, I guess just another note with the FE mesh, if you have a large model and your calculation is taking a very long time, that might be due to how fine your FE mesh is. So you can increase the fineness of your FE mesh as much as you want, but just keep in mind that at some point you might get diminishing returns and longer calculation times. So, but yeah, we can move on to, let's see. So before we take a quick break, I'll just show you within this results tab here. I'll clean it up a little bit and close or compress these folders. Right now I have both my surface internal forces and member internal forces being shown. If we can turn on our sections here, and now we get a nice section cut moment diagram of our moments here. So yeah, now you can see the results, and maybe also you can see the slight difference in accuracy, or the slight difference in results between our different size FE mesh. So here we get a peak moment of -6.592 for this smaller FE mesh. You can see that increases by just a little bit to 0.593 for the medium sized, and then the larger size FE mesh we have 0.594. So again, if you get small changes in results like this FE mesh size would probably be sufficient for this plate. So yeah, let's take a quick break, take a quick 5-minute break so we can resume this at 11:10. All right, so we can resume. So I'll just put this back to RFM. Yeah, so we left off with showing the results for our section cut here. And like I said before, we can move into, we already talked about FE mesh a little bit, but I think I can explain maybe a little bit more. So the size you pick for your FE mesh, like what we mentioned before, affects your results. And so, like we mentioned, you can go to calculate and you can go to the calculation parameters. And once that pops up, now you can go to global calculation parameters. And what we're going to do is for this, we're going to deactivate the shear stiffness for our members here. And this is important because if you're trying to compare hand calculations, like you might do in RFEM, sorry. So if you're comparing hand calculations or trying to compare hand calculations to the calculations in RFEM, this option is always activated by default, and it's always making calculations based on the shear stiffness of the members. So once this is done, we will have to click OK, and it's going to say what that action did is going to require me to delete my results. Do I want to continue? I'll hit yes. And now I can rotate my model again. And so once I've done that, now it's going to make me recalculate. And then once I recalculate, you'll see that the results are going to change just a little bit, and that's the results are mostly going to be the bending moments, because instead of RFEM taking into consideration shear stiffness, it's just going to assume an infinite rigid stiffness for the shear. And I'll get into that just in a little bit. So basically, this is because the methods used in school, like I said, assume a infinite shear stiffness, when in reality there are some shear deformations for bending. So just keep this in mind when comparing hand calculations of deformations with RFEM. So now back to the PowerPoint, we can go over some plate theory. So now I'll take this back to the PowerPoint. So now let's go over the plate theory. So get back to that slide. So basically, this is going to be these first theories are going to be analogies to beam elements. So the first theory is Bernoulli's, and with this theory, and then the second theory is the Timoshenko theory. And the assumptions made for Bernoulli's is that the cross sections always remain in plane and are perpendicular to the member axes. And then the second assumption that's made is that there are no considerations of shear deformations, and that the shear stiffness is completely rigid for our member. When it comes to the Timoshenko theory, the cross sections, similar to Bernoulli's, we assume that the cross sections remain in plane and are perpendicular to the member axes. But we assume that the shear deformations are taken into consideration and shear stiffness is limited and isn't completely rigid. So this is the more realistic theory, and this is the one that you might use in school. So now I just want to show a graphic to represent what I just mentioned in the previous slide. So here you have Bernoulli's, and here you can see the deformation is perpendicular right here to the member axes. And then for the Timoshenko theory, we have an additional angle. And so we have also, that comes with also additional deformation. And that is due to the additional shear deformations or shear stiffness that is taken into consideration. So these two theories we can apply to plate theories. So an equivalent analogy for plate elements, we have the Kirchhoff theory, and then we have the Resner-Mindlin theory. So again, the assumptions for Kirchhoff is similar to Bernoulli's theory, but for plates. And the similar theory from the Timoshenko theory is the Resner-Mindlin. And we can basically make these assumptions for the Kirchhoff theory. So we assume that it is a geometrically linear calculation for small deformations, and we'll be using a linear elastic material, basically Hooke's law. We assume that the cross sections remain flat with no warping, they have a constant thickness, and there is no consideration of shear deformations when it comes to the Kirchhoff theory. For the Resner-Mindlin theory, we assume basically the same for the Kirchhoff theory, but the only difference is that the shear deformations are considered, and we make a consideration of transverse and lateral strains. So if we move to the next slide, we can get a better look at what transverse/lateral strains means, like considering that. So here we have one beam, and when a tension force is applied to it along its length, the cross-section will shrink with regards to its height and width. So basically, the factor mu here is what takes this into consideration for our height and width. And just to summarize, for the Kirchhoff theory and Resner-Mindlin theory, Kirchhoff normally yields great results when very thin plates are used, for example, concrete slabs. You also have to keep in mind that this only considers pure bending load-bearing capacity, and this is just basically a simplified approach. For Resner-Mindlin theory, the considerations for shear deformations are there, and this is better for thick plates. And also, shear influence from components is relatively high. There's also a significant error when neglecting shear forces, and this is just better for more accurate shear forces and is a higher value approach. In my opinion, the Resner-Mindlin theory is what you should be using most of the time, but I just think it's just good to know the difference between these two theories. So now what we can do is move back to the program. And in the program, within the program, we can go to calculation parameters. And once we open up calculation parameters, you will see that under options here, the plate bending theory is by default set to Minlin. So this theory, like I said in the PowerPoint, takes into consideration shear deformations. So we can just keep that the same. So, or we can also change it and we can get a view of maybe how the results change. So we'll change it to Kirchhoff and taking into consideration, and so we won't take into consideration shear deformations. And then we can click OK. So before we do that, maybe get a quick glance of what these results look like. And then we can click OK. It's going to ask me to delete the results because I changed that theory. So I'll click yes. And now I'll rerun my calculation. It'll run the calculation based on the based on the Kirchhoff theory.
Alex, we have a quick question.
Yeah.
Maybe while we're waiting for this calculation to run.
Okay.
We have a user that says, is it possible to change the units of the values in the results?
To change the, yeah, it is.
So basically, yeah, it just can you change units for your results as well?
Yeah, so that's something I should have mentioned in the beginning. So you can change your units of your results and just like the units in general by going up here to options. And then you can go here to units and decimal places. And then this dialog box will pop up, and within here you can change the units of any result pretty much, basically. So up here you have tabs, and you can go to results. And then here you have deformations. You can change the results of your internal forces here. So you have a drop down, you can change between any of these units if you like. So you can also change your decimal places as well. And if you want to change between imperial and metric, you can do that at any time throughout your modeling as well. So yeah. So those results ran, and maybe you can remember a little bit from the results before, but you can see that they've changed slightly, maybe by what was it, 0.1 or 0.2, 0.1 or 0.2 kip per feet. And so what I can do is, now that we ran that, we can also move on to another question. So I'm going to go back to the PowerPoint, and I would just like to give a quick question. One second. So now this question should pop up in the PowerPoint. And if you just want to, you can enter your answer in the chat. And I'll just, again, give another 30 seconds to a minute for that. All right, so it looks like a lot of people are saying, the majority of people are saying B. It's about a mixed result. So the question is, what happens if the shear stiffness is activated? So basically in RFEM, the shear stiffness is activated by default, and the correct answer is A. shear deformations are considered. So B, increased accuracy in results. This is somewhat true. So that is also could be the correct answer, but the correct answer is A, shear deformations are considered. C, the shear stiffness of elements is infinitely rigid. That would be true if the shear stiffness was not activated. All right, so, and then I just have a second question that I will throw up, and that will come up. Sorry, 1 second. Here it is. Actually, for now, we'll leave this question for later on. So we'll just jump back to the program and continue with the model. And yeah, so now we can move on to the Euler case 1 example. So this concludes the plate theory and the continuous plates. So now we can just move on to the Euler case 1 example frame. So what we can do is we can open up a new model. We can also save our model for our continuous plate by hitting the Save Model button up here. And that'll save our model. And now what I can do is I can click on New Model. And within this new model general data tab, like I said before, we can just type in our model name. So I'll just name this one Euler case 1, example training. We don't have to add a description. We don't really need to generate generate combinations automatically. So it'll also be a 3D model, and everything here is set by default, so that's good. So we'll click OK. And now we have our blank workspace here. So what we're going to do is just create one single member, and this is just going to have a new cross section. So what I can do is go up here to new single member. I can click on that, and now I can create my cross section here again. So I can go to import from cross section library. And then it's going to be an I section. So I'm going to click on I section. And for this example, I will be using the manufacturer / standard group AISC, AISC. But again, we have the Canadian standard as well as Eurocode and a couple others, or a long list of others. So, but for this, I'll just be using the AISC, and I'll be using the latest standard. And then up here, I can go through W sections, and this section is going to be a 12 by 35. So I'll click on 12 by 35, and then here we can select the material. Right now, it's automatic, or by default, it's selected steel A992 based on the AISC. So that's good. We can also get our cross-section dimensions up here as well. So I'll click OK. And now you'll see that our cross-section has been defined. Also, I can take a look at my cross-section properties by clicking on this eye here. And we can get our properties here as well. I'll close out of that. And then I'll click OK. And now I can draw my member. So maybe I want to draw my member perpendicular to this grid here. What I can do is I can check off this box here called length and direction, and I can set this perpendicular to work plane if I want to draw it perpendicularly. Or what I can also do is just change my work plane up here using these buttons. So right now it's set to work plane in the X and Y plane. I can change my work plane to the YZ plane, or I can change it to the XZ plane. I'll keep it on the XZ plane, and now I can just select my origin here by left clicking, and I want this column to be 30 feet high. So what I can do is simply just go up here, left click, and now my column has been drawn. I can right click to cancel out of this, and now our column has been drawn. So now the next thing we want to do is just add in a rigid support. So I can draw from left to right, or highlight from left to right this node here. I can go up to nodal support, and right now it's set to hinged. Instead of having to define a rigid support, what I can do is just hit this drop down and select rigid, and you can see that all of the degrees of freedom here from translation and rotation are all fixed with these check marks. So now I can click OK, and I can zoom in here and you can see that my rigid support has been added. And now our Euler column 1 has been created. And what I can do is create a new load case for it. So because I need to add in loading, I can go up here to new load case. And I can just name this load case test. And the action category is just set to dead. Again, we're going to deactivate self-weight just for hand calc reasons. Normally you want to keep self-weight activated at all times for design. So we'll click OK. And now we can create our new nodal load. So to add a nodal load instead of a member load or surface load, we have a button here called new nodal load. We can click on that. And this box should look pretty simple. So we have our node selected up here, and then we just want to tell the program the force and what direction it's going to be in. It also looks like I'm still in metric I have kilonewtons, so let's change that down here in this units button at the bottom. So I'm going to just change this back to imperial. I'll click OK. Oh, it's asking me. Yep. So for this load, we're going to add in a -5 kips in the Z direction. And you can see that loading has been shown here in the graphic. And then also I want a lateral load in the X direction of 2 kips. So we'll add that. We'll click OK. And it looks like I had my node down here selected before I went into my tool up here. So what I can do is I can just double click on this loading and change the node. Or I cannot change the node there. So what I can do is just drag this loading to this top node here, and there we go. So now that our loading is on the top of our column, I also want to make sure that my column is still 30 feet tall. So what I can do is go up to tools, and I can go to measure, distance between 2 nodes. I can click on these 2 nodes. Yep, so it's 30 feet tall. I'll click OK. And now we can, and so yeah, now what I want to show you is something important. So this is very important for calculations of structures within RFEM. What I can do is click on Calculate All, and I can run the calculation for this column. And now you'll see that my deformation is shown here, my resultant deformation. I can also go here to member and again show my internal forces. I can show my moment about the local y-axis here. I can get a elevation view of that. And so also when you look at, we can take a look at our deformation in the x direction, 3.782. That's 3.782 inches. And now I just want to show you, I want to show you how this linear or first order calculation differs from a second order calculation. So just to clarify on that, if I go to edit load cases / combinations, and we're looking at this load case that we've just put loading on and we've created. If I go over here to my calculation parameters, you can see we get our method of analysis right here. So generally, load combinations are calculated based on a first order analysis, and load combinations, which we didn't get into, but load combinations are calculated based on a second order analysis. And maybe you recognize this information from the name P delta. So the second order analysis takes into consideration large P delta and little P delta. And what we can do is we can change our load case to a second order analysis. And then I can click OK after doing that. So basically a first order analysis, says to make or defines the equilibrium of the beam based on the underformed system. And the second order analysis bases the equilibrium on the deformed system, so that the deformation and bending moment is going to be increased because of the larger deformation. So if I do that and then I click on calculate all, you should see that the deformation has increased from 3.7 to 3.9 inches. And also our moment here at the bottom has increased from about 60 kip feet to 61.6 kip feet. And this is because of the P delta effect. So since the deformation has increased, the implied axial load, the applied axial load has an increased moment arm since the deformation increased, giving us a larger moment here. So, keep in mind you will get two different results with these different analyses. One note also, members in RFEM, like this one, are determined to be a beam or column internally based on how the loads are applied. In this case, we have a column because of the majority of the forces are axial that are applied. Maybe just quickly we can quickly go over member types, just the basic ones. So if I double click on my member here, you can see that my member type is set to beam. So that takes into account beam or column. We also have rigid for infinitely rigid stiffnesses, and we also have ribs, truss members, but we won't get into any of these types today, but they're just good to know. If you're designing a beam, or if you're drawing a beam or column, then always keep the member type as beam. So now we can change the loads at any time, basically. This will erase our results, but I'm going to change my loading to only 100 pounds in the axial direction. So I'll double click on my loading here. And then what I'm going to do is just, like I said, change this to 100 pounds or -0.1 kips. And I'm going to set my lateral forces to 0, click OK. And now you can see that that loading has changed and decreased.
Hey, Alex, quick question.
Yeah.
I know you showed this at the beginning, but we had a question. If you could just review it again, how to automatically account for self-weight.
Okay, yeah. Yeah, so I know I've been turning off self-weight or not been accounting for that throughout the training. But if you want to automatically take into consideration self-weight, I can go back into my load cases and combinations here. And then under dead load, the action category is always going to have self-weight activated by default. And what this means is for this load case, a -1 factor is going to be applied to the self-weight of the structure. And that's going to that's just going to take into consideration that force that's being applied to your structure. So if you have multiple load cases, you just only need to set or keep self-weight activated for your dead load case, and that will take into consideration for your whole structure. So
perfect. Thank you.
You're welcome. I'll click OK. And yeah, so if you're ever confused about the self-weight and how it's being applied, another tip is you can go into your display tab down here in the project navigator, and you can go to loads, and then you can always display your self-weight. So you can turn that on if you'd like, but by default that's turned off. So yeah, so now that I decreased the loading on our column here, what we can do is we can go into our RF stability add-on module. So that will be something that all students have access to. So I can go down here to add-on modules, and you're probably going to have a long list of add-on modules here. I favorited some of mine, the most ones that I use most frequently. If you're having trouble finding the RF stability analysis add-on module, you can go up here to add-on modules, and then you can go to others, and then you can go to you can go to stability, and then you can go to RF stability. And so basically this all of the add-on modules look pretty similar to this. All the add-on modules are basically just a dialog box. And within this dialog box, it'll take all of the data from RFEM, such as materials, cross-sections, members, everything. You don't have to worry about redrawing or modeling anything. It's all taken from RFEM. And this add-on module, RF stability, is very useful. So what RF stability, just to explain, RF stability uses the help of eigenvalues and different eigenforms to perform a stability analysis. So just some background information. Euler was a mathematician who came up with different cases to show the critical factor along with the critical load and lengths for a structure. So this is something every stability analysis does. And in order to get the different buckling cases, I will just have to simply deactivate the minimum initial pre-stress for cables and members. And then it is also important that we activate the division. It's already by default, but activate the division for straight members, so I can keep that checked. And then there's also this edit button right here next to that criteria. I can click on that edit button. And then just to increase accuracy, within these options, the only thing I want to change here is the minimum number of member divisions. Instead of 2, we're going to set that to a value of 10. And then I'll click OK. And now what we can do is go back to RF stability, which I did clicking OK. And it is important to change that value from 2 to 10. And now what I can do is hit calculate. So once I hit calculate, what RF stability will do is take my internal forces and everything, and members and cross sections of materials, and now it'll give me a load factor and a magnification factor here for my different eigenvalue numbers. So the critical load factor is the amount you would have to multiply the loads in order to get an unstable system. Or it can be looked at as you could look at it as a total percent of the loads your structure can take. So basically right now my structure could take 135 times more loading than it is taking right now. And then we have our effective lengths in the next results down here. And we can also view the results graphically and take a look at our eigenvectors. So I can go down here to graphics and need to hide my panel. So we have our panel here on the right-hand side. And what I can do is go through my different eigenvectors. So what I can twist this around. And then what I can also do is go to display here. Display here. Select color cross sections, and yeah, so this gives you just a better idea of the deformations, and then I can cycle through those different eigenvector numbers. And then, so yeah, that just gives us a better look at the first buckling case or buckling form. I think it is clear also that the column will first be unstable in the weak axis direction. So basically the axis of this column is in the y direction or about the local z axis. So what I can do for clarification is just turn on my local z axis. And this is because the smallest moment of inertia is in the y direction or about the local z axis. And to double check that, I can double click and I can go to info about cross section, and you will see that my smallest moment of inertia here is about my z axis, 24.5 inches. 24.5, and then so that just gives us an idea of our moment of inertia there, giving us our weak axes. And now we can jump back to RF stability by simply just clicking on RF stability here. And we can take a look at, again, our effective length factor here by going to effective lengths and critical loads. So we have our weak axes and strong axes for both our effective length and effective length factor. We also can show you what it looks like if the structure is unstable. So maybe you have a structure that's unstable because the loading is too high. So for example, what I can do is click OK. And then I can go back to my LC1. And what I can do, so let's say my structure is unstable, I've increased my loading, it's too high. Maybe I'll make it, I don't know, negative 14 kips. And then I'll click OK. So now my loading's too high. We can see that by clicking, by calculating the results. Keep in mind, I also still have P delta or second order analysis on. So you'll see something like this. You'll see an error message, calculation errors and messages. It'll say something like the stiffness matrix is singular, and it'll explain that it's possible to calculate the critical load factors and buckling in the add-on module RF stability. So what we can do is close out of that, and the first thing you want to do is make sure that your load cases are being calculated based on a first order analysis. I want to change mine back to a linear analysis. So now that I've done that, I can jump back to our stability. And then within our stability, I can keep all this the same. You'll see that the load case / combination that it's referring to is LC1. I'll click calculate. And now once that's done calculating, you should see that my critical load factor here is below 1. So basically, since my critical load factor here is below 1 at 0.966, that means that my structure can only take about 96–97% of the loading that is applied. So now I would just like to go back to the PowerPoint real quick, and I just have a question I hope you guys can answer. So what I can do is open up the PowerPoint, and I can pull that question up. And that should come up right now. And then I'll just give, sorry, 1 second. And then I'll just give you guys, again, about a minute to answer that. We can go over it. All right, awesome. Thank you for the answers. So it looks like some people said true, some people said false. So I'll read the question. The critical load factor specifies which factor can be used to increase the stiffness until the structural system fails. So the answer to this is false. The correct way to read this would be the critical load factor specifies which factor can be used to increase the loading until the structural system fails. So just to reiterate that, I can go back to RFEM and with an RFM, so yeah, the critical load factor here, this lets you know that your loading and not your stiffness needs to be, well, you can increase your stiffness as well, but this lets you know that the loading that you applied to your structure, if this number right here is below 1, then your loading is too high, and you can only take this much loading, or this percentage of loading. So now what we can do is go back, click OK. Since our critical load factor is below 1, what we'd want to do is just decrease this loading in our LC1 up here. Again, you can change between, or you can select your load cases and combinations up here with this drop-down window that tells you which one you're under. And now we can move on to modeling our moment frame. So since our critical load factor is below 1, I'm going to decrease my loading to -5 kips. I'll click OK. And now I want to change the height of our column So if I want to change the height of this column, I can simply highlight this node here, double click on it, and then I can change the height by easily changing the Z coordinate to 10 feet. So this will be the height of our moment frame. Actually, before we do that, let's save this model. This will be our Euler case 1 model. And then what I want to do is go to File. I want to save a copy of this model. I can save this copy as our moment frame. And then what I can do is open that copy. And now we can turn this column into our moment frame. So I can highlight again this node here, double click on it, shrink this to 10 feet. And now I just want to make a copy of this column. And so I can just highlight it, the whole thing, hold Control, and then just simply drag this column. Want to make that 10 feet in the negative X direction. Or also we can change that to, yeah. So I want to make that in the positive X direction, and it's going to be 10 feet away. And then what we can do is create a beam spanning between our columns here. I can also just hold Control and, oops. I can Control Z to undo that. What I can do is just hold Control and move this loading over. And now I can draw a beam that will span between the two columns. And this beam is going to be a 8 by 15, W8 by 15. So I'm going to import that from our cross-section library. I'm going to go to I sections. And then what I'm going to do is go down to 8 by 15. Again, leaving all these filters the same. So that'll be an 8 by 15. I'll click OK. And now we can draw our beam here. And that'll span between these two columns. And I can right click and cancel out of that. And now what I can do is run my calculation. So we just turn that column into a simple moment frame. And now we can get our global deformations and see what those look like as well. We can also take a look at our internal forces by checking off members here. So we can look at the axial forces. And then if we want to get a better idea, we can also add in some lateral forces as well. So we can add in 2 kips in the X direction for both of these. And rerun our calculation. So now we can get a look at our moments from our lateral loading. And then we can also go down here and we can take a look at our support reactions. So we have our support reactions here, and we can also get a look at our moment reactions as well. And those are defined based on the double arrows here. Another good thing is you can turn off your grid as well if you just want a cleaner view of your results. You can turn off, you have these buttons down here to turn off your grid. And then what we can do is go to our stability. And then we can take a look at our critical load factors. So we can hit calculate. And we can see that our critical load factor is pretty high, which is good. We can check out our eigenvectors. We can get an elevation view. Elevation view of that. And we can cycle through these. You can see we have some out of plane deformation, so maybe this frame will have some lateral supports, some pinned lateral supports up here to keep it in plane. So what we can do is hit new type of support. And then this support would allow it to move in the Z direction and the X direction, but keep it in plane in the Y direction. And the rotation for this pin support will be all released. We'll click OK again, and then we can hit calculate. And RFEM will run through these calculations again, and then we can take a look and see how our eigenvectors have changed based on the supports we added here. So you can see that we don't have any out of plane deformations at the top here. And also I'm sure our critical load factor has changed. It has increased from 20 to 164, so just adding those supports has helped a lot. And so that's the end of the calculations and modeling for our Euler case 1 example and for our moment frame. So right now we'll just take a quick 5-minute break again. And then when we come back, we'll resume with the concrete model, and maybe we can have a little quick discussion if anybody has certain questions that they would like to have answered. So we'll come back at 12:09. All right, so we can resume now. Yeah, so now that we finished the moment frame, we can get into modeling the concrete structure. But before we get into that, I wanted to just know if anybody had any specific questions they wanted to go over that either Amy or I could answer before we move on. I'll just pull up.
So we have a quick question just saying, how do we add lateral loads? And I do believe in your last example, you had applied a lateral load to your column. So
yeah. Do you just want me to go over how to apply those?
Yeah, I think I'll just explain to the user quickly that the lateral loads can be applied the same way as gravity loads. So Alex has been applying loads in the global X, Y, and Z directions. So lateral loads would be in the X or Y directions. You can see here 2 kips, for example, is in the lateral direction. So that should answer the question.
Yeah. Yeah. And so, yeah, when you add a new nodal load, when you click on new nodal load, you'll see that you have options for the X direction where you can add your lateral loading in, and then you can see how the lateral loads work with the global coordinate system up here and everything. So yeah.
To specify wind and seismic loads is what he was looking for, and seismic loads can be done through our add-on module RF Dynam Pro, which Alex won't be able to get into today, but we definitely have plenty of resources online that can answer that. Wind loads, Alex, you can show how under the tools generate loads, and then there is the option here for wind and snow loads according to Euro code primarily and the US codes. But these are really for general rectangular structures. So if you have anything outside of a rectangular structure, you'll need to manually apply it as we've been showing.
Yeah.
So I think that should answer that question.
Yeah. Yeah. So, I mean, basically, yeah, when you create, yeah, like Amy said, those are basically for like pitched roof for rectangular buildings. But I guess you can also just create a new load case as well, and then just create your wind load case and just add in your lateral loads or lateral uniform loads as well. So
good.
Yeah.
Another quick question, going back to the beginning, when you create a new line or maybe a new member, how do you modify if you notice your dimensions are not accurate?
Yeah. Yeah, so creating a new line, again, you can use this tool. If the dimensions are not accurate, I guess I would interpret that as the length, maybe, or if you're talking about the length is not accurate.
Yeah, I think just showing how to modify, node coordinates or dragging and dropping, multiple options.
Yeah. Okay. Yeah. So I mean, right now the cursor when you click is always gonna draw the line in the grid that you have placed. This like the work grid, and right now mine's in the XY plane. So I'm going to draw in the XY plane. Maybe if you click and then you just want to type in your coordinates up here, you can do that. And you can just type in the coordinates you want the end of the line to go to. Also, if you want to just type in, you can see my length is highlighted right now as 9 feet. But if I just want to type in 10 feet and I don't move my mouse at all, I can hit enter and that'll give me my magnitude and the direction I have it pointing. So yeah, those are just a couple options when doing new lines. Another good option is to check off the length and direction here, and then I can just type in, I don't know, 10 feet And you can see that my line will be placed perpendicular to my work plane here as well, if I click. So yeah, those are a couple options for creating new lines. Yeah.
Okay. I think that answers a majority of the questions for now, and we'll just continue to ask them as they come up, or I'll answer them individually.
Okay, awesome. Yep, good questions. Thank you, Amy. So yeah, back to the PowerPoint real quick. We'll be modeling this concrete model, and we'll just start going through this. We might not be able to finish it, but I think it has a lot of I think it goes through a lot of great methods to modeling and things, and good tips and everything. So we'll just go back to RFEM. And now that RFEM's up, we can simply just create a new model. So what I can do is go up here. What I can do is go up to the new model button. And once I click that again, we have our general data where I can just enter the name, concrete model. And I'll just name this one concrete model training. And for this model, we can keep everything the same. For this one, I would want to generate combinations automatically based on the standard. And then it'll be a 3D model, and I'll just make sure that my local axis is facing downwards, because this is important for the atom modules. And so now that that's all set, I can click OK. I also want to go up here and just go to File, Save All, make sure all my models are saved. Also keep in mind, maybe if you unfortunately have a program crash, that if you didn't save your model, that there's always a backup file that's created automatically in the background. So don't be worried if you've worked for a while and didn't save and then something happens. So it's always a good, there will be a backup. All right, so now my models are saved, and what I can do is now start off with the slab that my building is going to be sitting on. So this floor slab is basically just going to be a rectangular slab. Something else that I might want to do before I get into drawing this rectangular slab is I just probably want to just set my grid to dynamically according to the size of the model. I'll just set it to that. So that changes automatically. I don't have to worry about expanding that at all. Also, my grid points are still 1 foot by 1 foot. I'm not sure if I mentioned that before, but the grid points are all spaced by 1 foot. Actually, I'm in metric right now. I think I might have set my program to default to metric in the beginning, so let's change that. I want to change, so we'll go to, again, load save profile, and if you want to change the default of what your units are in, I'm going to check imperial, click OK, and then this button right here sets your default, so I'm going to set my default as imperial, click OK, and now you can see that my spacing should change to 1 foot by 1 foot. There we go. So yeah, these grid points, you can change the spacing of them. I'm going to leave them as default as 1 foot by 1 foot. And now I can begin creating my slab, my floor slab for this building. So I also want to turn off another option that we have in the program. So if I right click, and if you right click, you can see this option that says auto connect line / members here. I'm going to turn that off. That's on by default. And what that does is when you have a line intersect with another line, the program will automatically separate those lines into separate members and connect them and add a node. And you'll see a better example of that when I get into creating the walls. So I'm going to go up here to new rectangular surface. And now I have my thickness here. So I'm going to make that 12 inch, or I'm actually going to keep that as 8 inches. Again, we have our materials. So I'm going to go to import to material from material library. And I want to make this, again, concrete. And I'm just going to make it 4,000 PSI concrete. I'll click OK. And I'll click OK again. And now I'll click on my origin here. And this slab is going to be, this slab's going to be 46 by 40 feet. And I'm just going to go up here, and I can, instead of having to rotate my model, I can just hit the top-down view here, and I'm going to hit reverse in Z direction, so I'm looking from top down, and then this is going to be 46 feet in the X direction, and then it's going to be 40 feet in the Y direction in the height. So I can move that up, 46 by 40, and I can right click anywhere or hit escape, and now you can see we have our slab here. So now that we have the slab or the floor, we can add in work on adding in our columns. So the columns are going to be perpendicular to the slab. And I think the best way to do this is to simply just highlight our corner node or our origin here. And then it's going to be, I'm going to just make a copy of this origin or the node there. And I'm going to go to move and copy. I'm going to make one copy of that node, and then I'm going to move it 2 feet in the X direction and 2 feet in the Y direction. And now that I've entered that information, I can click OK, and you can see I made one copy 2 feet in the X and Y direction. So that'll be the placement of our first column right there in the corner. And now I want to do the same thing for 2 more nodes. I want them to go in the X direction. I'm just going to click on that node, and I'm going to go to move and copy again, and I'm going to make 2 copies of that node. And then I only want it to go in the X direction, so I'm going to type in 16 feet, and I'm going to click OK. And now you can see I made 2 more copies in the X direction of that node, and that's again where these nodes are going to be the base of our column. And so what I can do is I want to have one more column here at the corner. This is going to be symmetrical, so we want it to be 2 feet away from this node here. And what I can simply do is just hold Control, left click, and then just move it over there. And you can see, maybe it might be hard on your side to see, but there are the grid points here that I can just snap to as well. So there we go. We have our first row of our nodes there that are going to be our columns. And now what I want to do is what I'm going to have is 3 rows of columns here. So I can just rotate this model or this floor here. And then I'm going to simply just hold Control and select my nodes. And what I can do is make a copy of those. So the move and copy tool is pretty useful. So we can make 2 copies of this row of nodes and just move those 13 feet in the Y direction. I'll click OK. And now you can see that we have our additional 2 rows there. So after that, the arrangement of column nodes is right here as follows. Something else I would like to mention is just under the display tab, you can, once you have a large model and it includes a lot of different nodes and lines and elements, if you go to your display tab here, you can check off numbering, And this will just give you numbers in your work window. So you can see like I have line 4 here and then different numbered nodes. So it makes it easier just to stay organized. And also for reference as well. So now we want to define our walls. And to do that, we can simply divide our lines here like we did with the plates earlier. So we can right click on line 4 here, and what we want to do is go to divide line and then go to graphically, and then this wall is going to be placed right next to this node here. So I'll left click and divide that line, and now you can see I'm still in the divide line tool. I can right click out of that. And now we can do the same thing for this line up here at the top. I'm going to click on it. I'm going to right click, select divide line graphically. And maybe just to reiterate what graphically means is you can see I can just snap or place the node wherever I want to on the line graphically using my cursor. I'm going to place it right here. This is going to be 28 feet from the start. So I'll place that, and now you can see that we have 2 lines now with the node there placed at 28 feet from the start. And also again, if you're confused about the orientation of your line, you can see the arrow here. When you hover over your line, this red arrow tells you the direction. Now what we can do is we can move on to creating our semicircle surface, which is going to be used for our spiral staircase over here. And we can go up here to new rectangular surface. And instead of clicking this, we can hit this drop down button here. And you can see we have a list of different shaped surfaces, along with being able to do a polygon, or you can select the boundary lines of something and create a surface as well if you don't see the shape here. And what we want is semicircle. Similar dialog box, everything here is fine. We can keep that. And now I can just simply draw what is going to be the radius of this semicircle. So the radius is going to be 7 feet. So I'll start at node 3 here at the corner. Actually, that's not where I want to start. I want to start 7 feet away from that node because you start from the center. So it's going to be 7 feet. That'll be at 4640. Or my mistake, that'll be at 4633. So we'll start at 4643, draw this so the radius is 7 feet, and we'll end it at the corner there. And now you can see we have our semicircle surface here attached to our rectangular. And so now, after surface 2 has been created, we can work on our ceiling slab. And this should be pretty easy since our ceiling slab is going to be symmetrical, or basically the same as our floor slab. What we can do is we can highlight our floor here, and then we're going to move and copy it. And something to keep in mind is that there's going to be a clear height. So example for this concrete building, there's a clear height of 11 feet between these 2 slabs, between the floor slab and the ceiling slab. And we also want to take into consideration the thickness of these slabs. So what we are going to do is we are going to take half the height or half the thickness of each slab and then add that to our 11 feet. So we take into consideration the thickness, and that's going to be 11.83 feet in the Z direction, and we're only going to make 1 copy. We'll click OK. And now our ceiling slab is created, which is not the correct height. So to change that, I can Control Z. And I'm going to redo that, move copy. Oh, I typed in 1.83, that makes sense. So 11.83 is what we want. And now our ceiling slab is created with the correct distance between them. The next thing we want to do is to maybe check out some different views. So if we click on isometric, we get our isometric view here. Maybe we want to take a look at a different way, different perspective, so we can check on our perspective view. And then we can look at the reverse in the Z direction, and we can see if we didn't have perspective view on, you wouldn't be able to see that there's two slabs here. So if you turn that on, you can get a better look at maybe some elements that are lying on top of each other. Now we want to create the walls between these two slabs. So to do that, we're going to first merge these two surfaces here. So what I want to do is I want to divide this line here. So I'm going to right click on line 16 here, and then I'm going to divide it. And I'm going to divide it by distance. And I wanted to divide it right in the middle. And now that that's divided in the middle, we have two different lines here now, 16 and 17. And so now what I want to do is, if I want to connect these lines here, connect this line to this line at node 40 here, you can see that this line is one whole line. So if I go up here to this tool called connect line/members, I'll click on that and I'll highlight my node there. And you can see that what that did was split that line at that node and connected them, creating two different lines and an intersection. So now we can delete the surface, our top surface here for our ceiling. And so we'll select the two surfaces by holding Control, delete. And the reason I did this was so that we can delete these two lines here, 16 and 17. I have two lines lying on top of each other, so I'm going to delete 16, 17, and 18. I just do that by clicking on them and hitting delete. We also can delete those lines by going to the project navigator, just for example. So if I wanted to delete these lines, I could go to data, and then I could go to lines, and then I could just click on or hold shift and select 17, 18, or 16, 17, and 18 and hit delete. And now we're just left with this outer boundary line and node 40 here. So now what I want to do is just recreate the surface by going up to my surface tool here. And then I can hit this drop down and then I can select boundary lines. So this is pretty easy. This is a very abnormal shape here. I want my ceiling to have a thickness of 12 inches. Everything else is good here. All I need to do is select this boundary line, and you can see that the surface has been generated based on that boundary line. And we also kept node 40 here, which is very important, because now what we want to do is add in an opening right here for our spiral staircase, and we can use node 40 as the center of that opening. So I'll go up here to right next to the surfaces tool, we have an opening tool. And right now it's set to new rectangular opening by default, but if I click on the arrow next to it, I get my options for other openings. So I want a circular opening. And now I can just click on node 40 and automatically the circular opening will be set. So right now my step or my selecting this graphically is a little bit crazy. So what I can do is go up here to this window that I have open. I can select step and I can make the step just 1 foot. And now you can see that I can create my opening, and each time I move my mouse, it's just 1 foot. And so then I can also just type in the radius of this opening, which will be 6 feet, and I can hit enter. And you'll see that RFEM automatically integrates that opening into the surface here and gives us a nice symbol for our opening as well. So I'll hit exit, or escape, I mean, and that tool will close out. And now we can get into defining our walls. So maybe I'll go back to an isometric view, and I can rotate the model so the staircase is in front of me. And now what I want to do is create some new lines. And I also need to create some new nodes here on this line. So I don't need to create a new node there. I can just go up here to new line. And basically what I'm doing is just connecting the floor to the ceiling with this line here, which will act as our wall boundary. And this is going to be, let's see, about 7 feet away, or 7 feet away from node 20 here. So that will be at 4619. So we'll go to 4619. I'll draw up to the line, and again, you get that nice symbol there, that snap point for perpendicular, kind of like AutoCAD, and there you go. Now that line's there, it's perpendicular, and now we just want to create some other lines for our for our boundary, for our walls. So the next one will be 12 feet away from node 3. So we'll go over here to, let's see, 3440. So that will be right here. And now I can go up to my line here, get that nice symbol with the perpendicular. And now we have those 2 lines for our walls. And now we can simply just connect the rest of we don't have to create any more nodes here, or I mean, we can just simply connect our nodes here, 3 and 23. Let's see, 20 and 40. What else? 40 or 4 and 24. Oops. Looks like I created a line there. Control Z. I can go back up to new line and just connect 4 and 24. And then we also want to connect 18 and 38. And also 17 and 37 here. And again, these are just creating our boundaries for our walls. So you'll see now that we have our lines here, but one last thing we want to do is connect all these lines and split these lines at their connections. So we can go up here to connect lines or members, highlight the whole model, and that will split our lines at those intersections. I'll right click out of that. And something else to note, alternatively, instead of, if you've turned, like we did, we turned off auto connect line / members in the beginning. If you're drawing your line and you just want the line to split the intersection there, you can go here to detail settings, and then you can just select auto connect connect line / members if they contact here under your line drawing. So you can keep that on if you want. We can exit out of that. And now we can create our walls. Pretty simple. We'll go up here to select boundary lines. And these walls are going to have a thickness of 8 inches. And everything else here is good. And now we can just easily select the boundary lines of the surface. So I'll start over here and I'll click each line. And keep in mind that you have to select the boundary lines as a polygonal chain. And what that means is if I select this line, I can't just select the line above it. I have to select a connecting line and go around. I can keep doing this for the rest of my walls. I'll rotate the model. Another good hint for rotating is if you hold in Control and then right click, you can also rotate, which is nice. So I'll create these walls. And then we need to create the wall for our staircase here. So to do that, since this is not in plane or it's out of plane, basically this needs to be a quadrangle. So we'll go up here to this tool called New Quadrangle Surface, and this is going to have a thickness of 8 inches. We'll click OK, and then this is basically like selecting boundary lines. So we'll select those, and now our quadrangle surface is created there. Let's see, and next we can now, let's see, we created our walls. The last wall we want to create is our inner wall here. So I'll go up to rectangular, and now I can just create a wall here for our inner wall, and that will go up to node 34. And that did not create correctly, so let's see. We want to go back, Control Z, and we want to make sure our work plane is in this plane. So this would be the YZ plane. So we'll go up to YZ. Again, you have your work plane options up here to change the work plane of your grid here. And then what we also can do is we can change the origin. So there's a button here called Set Origin of Grid/Work Plane. We can click on that, and then I can set the origin to node 18 here. And now I can draw that rectangular surface correctly. I'll click OK, and then I'll select node 18 and node 34, and now you can see that my wall there was created. After that, we want to now create our columns. So I can set my work plane back to the XZ plane. And then I'm just going to connect these nodes that we created in the beginning with a line. So I'll pick node 5 and 25. And then what you can do is you can turn lines into members basically by double clicking on them. And then going to member, there's some tabs up here. If you go to the member tab and then available, and then once you hit available, it's going to ask you, okay, what cross section do you want this to be defined as? We'll go to import cross section library. And this is going to be a rectangular parametric concrete massive section. And the dimensions of this are going to be 14 inches by 14 inches. Again, our material set here at the bottom, it looks like it's by the older standard by default, so let's go to import material library and make this for the newer standard. We'll click OK. So we have our concrete 4000 PSI. We'll hit OK again. And then we'll just keep hitting OK through these dialog boxes. And now you can see that my member here, my concrete column, that line that I connected those two nodes has been created or transferred into a column that we defined. And you can also see this in the table. So if I turn on my table up here, maybe we want to get a look at our cross sections in our table. So we can go open our table and we can go to members. And we can also, go to cross sections. And under the cross sections tab here, you can see we have our cross section listed. And we can also change this cross section from here as well if you would like. And yeah, you can also see up here what table you're in if you need to reference it. It's 1.13 cross sections. So I will close out of my table, and now we want to create the rest of these columns. And instead of having to manually do that, we can simply just, again, use the tool, highlight, and then hold Control, and then drag. And you can see that we'll just create a copy. And there you go. Now we have our first row of columns there. Another way of of selecting columns is going up to the special select option here. It's called special select tool. And what this does is allows you to select elements within your model based on these categories here. So let's say I want to, for example, select members. I can activate that, and I can activate all members, or I can select based on various options here based on material, type, number. We want to select based on cross section if we want to select all of our columns here, and we can select based on the 14 by 14 cross section. I'll click OK, and now you can see that all of those cross sections have been selected. And this is handy because now I can easily just hold Control, and all those are selected, so I can just hold Control, drag, and drop, and now all of my second row of columns is created. And finally, now we can just do one more column. We can just select a random one, hold Control, and connect 15 and 35 to the floor and ceiling there. And so the last thing we need to do for our model data is just add in this downstand beam. So there will be a downstand beam from the edge of this wall here, node 37, all the way to this column, node 35. This node 33 here is not needed, so I'll select that and delete it. And to add in this beam, I can simply just repeat what I did for the column. I can use a line, or I could just simply go to new single member. And then I can, under new single member, for this downstand beam, it's going to be a rib type. So I'll click on rib. And then for the rib type, I want to go to edit member type. There's an edit button right next to the type there. And we want to select the option on the positive Z, local Z side of the surface. And you can see that's under position and alignment. So you can see when I change these options here, it'll show me the slab, and it'll show me which side my rib is going to be on, as well as my local Z axes. So yeah, it's going to be on the positive side underneath the slab. And then also the integration width is going to be L/8 for side 1 and 2. And so now everything for all the options for our rib here are correct. So we'll click OK. And now I just need to change my cross section. And that'll load. So yeah, So once I create my cross section here, it's going to be 7 by 5, parametric massive section. So it'll be 7 inches by 5 inches, 4,000 psi concrete. We can hit this drop down and choose the latest standard. We'll click OK. And again, we'll click OK. And now we can draw. Oops. Now we can draw our rib, which is not correct there. Oh, I see. Okay, so what I can do is just exit out of that tool, go to new member, click OK. Need to redefine these. It's all good. And now it's asking me for the line. So I will have to create the line. And I'll connect the wall to the center wall there, and then to the column. And I'll go back to my new members, click OK. And then I'll click OK again. Everything's defined here correctly. And then I'll select this line here. And now we have our downstand beam. So now that that's defined, the next thing we want to do is add in an opening to our back wall here. So what we can do is we can go up here to our openings, rectangular, and then before we draw this opening, we need to make sure our work plane and origin is set in the correct orientation and position. So this work plane is going to be in the XZ plane. And then the origin is going to be at the corner here. And now we can draw our opening, our rectangular opening. And that's going to start at the top left here at a 1408. The coordinates, 1408. We can snap to grid points right here. And then we can just simply draw that. And that's going to end 503 right there. And now our opening has been created, our back window there. And the next thing to do is to add in supports for the structure. So all of the surfaces and all the model data there is created. We just need to add in the supports. And so the supports are going to consist of line supports. So we're going to assume that the foundation over here on this left-hand side is adjacent to another building. So we'll add in line supports there. And we'll go to new line support, create a new type of line support. And the only thing we want to be fixed with this line support is the translation in the Z direction. So all of these will be released. The translation in the X and Y will be released. Rotation will be released. The only thing we want is just support in the vertical direction. So we'll click OK. And again, and then I can just simply select my lines here and add in that line support. So the next type of support we want to add is a surface support, and this will be the foundation for our floor slab for surfaces 1 and 2. So I can just select surfaces 1 and 2. and go up here to new surface support. And within here we can go to, or within here we can define our surface support. So we can just simply create this foundation basically. So within the Y translation and the X translation, we're going to have a spring constant of 64 kip per cubic feet. And then in the vertical direction, we will have a spring constant of 640 kip per feet. And that's just going to represent the well, Y and X are going to represent the shear capacities of the surface, and then the Z is going to represent the soil. So for our nonlinearity, we also want to take into account uplift. So we select failure if negative contact stress in the Z direction. And this option basically corresponds to failure under tension. And that is if the slab is lifting up, that no more support will be provided. And that's a nonlinearity that's selected there. And the to model this appropriately, we would have to, well, this is all good. So we can click OK. And then we can move on to adding stiffness modifications based on the standard, or based on the ACI standard. But it does look like we're running out of time a little bit here, so I was just wondering, or we could take this time at the end here for a discussion. If anybody has any questions so far that they would like to have answered, we can go over that if there are any questions. So I'll just give some time if you want to enter them in the questions box there. Me and Amy can try to answer some if there are any questions that you would like to discuss. We also have an email, a tech support email, where you can send us questions, and also if you are modeling along, you can, if you're modeling along with the recording that will be sent out within the next day, then you can send us your model if you're having issues or have any questions as well. So if anything wasn't clear, the recording will be there, and we're also here for tech support as well.
We just have one, looks like a couple quick questions. The first is if an RF laminate webinar is coming in the near future. Mm-hmm. And Alex, you can explain maybe where recorded webinars are found?
Yeah, so yeah, I can do that. So if you go to our website, pull that up real quick. You can go to our website, and recorded webinars can be found under support and learning. If you go to support and learning, and then you go to webinars, you can click on that. Sorry for the slow computer load times here. You can go to scroll down here, and you can filter to past webinars. And then if you're looking for, let's say, RF laminate, you could go to product, and then you could go to RF laminate here. We could do a quick search, and you can find some, I believe Amy has some previous webinars on RF laminate that she just gave recently. So you can always go through these and watch them. They're really great, and for learning purposes, I'd definitely recommend them. So
yeah, perfect. So there is no plans immediately for an RF laminate webinar, but I presented one not too long ago. And again, you can find those recordings, as Alex mentioned, on the website. Mm-hmm. Yeah. The next question, user wants to know if creating a member for a truss is similar to the columns beams. So I think the member type truss is being asked about.
Yeah. So yeah, under those member types where the beam and the rib were, there is also a truss member type, and that's not the same as a beam or column. So the only difference between that is a truss member type will add pin connections to the ends of your members, and that will fully release the moments at those connections. So that's the main difference.
Yeah, and it is just as easy as instead of drawing a new member with the type set to beam, you can just easily use the drop down to change that to a truss or to tension only, maybe a rigid link, so many different options there. I think that will wrap up our questions, so you can go ahead and close out the presentation.
Yep. Yeah, so thank you everyone for attending. We have free online services on our website, like our GeoZone tool and FAQs and knowledge bases, and also we have models you can download from our website as well. Some other free online services. We have our YouTube channel, webinars and videos for great great informational videos, and also for just learning, and you can get your videos on the first steps of using RFEM. We also have our web shop with prices and also some trial license. And then this is also our website, like I mentioned before, and you can find our recorded videos and webinars, newsletters, events, conferences, knowledge-based articles, etc. And at the bottom here, we have our phone number as well as the tech support email that I mentioned earlier, where you can send in your models or questions if you model along later on and have issues. You can send that model to info-us@tulable.com. So thanks everyone for attending, and I hope you enjoy the rest of your day.